All right, welcome to lesson 2.17. So here we're going to continue working with the binomial theorem and actually look at it in a slightly different form, which is a little easier to write. So start off by completing 1 through 4 here, and it should be pretty simple. What you just want to notice is the patterns that are occurring so that we can make use of them to shorten the way that we write the binomial theorem. All right, so here is the binomial theorem, and just noticing the pattern that happens with the power of a. The power of a is changing by 1 each time, and it's starting at n and decreasing by 1 as we move. And that's on purpose, right? We want to go through and count up the total number of possibilities where we have an a chosen from each of these binomials and multiplied together, and then n minus 1 of those a's, so we have 1b, and then all the way out into the end where we have all b's and no a's. The pattern of the power of b is that the power of b is starting at 0 and increasing by 1 each time, so that by the end we've gotten to b to the n. In other words, that we've chosen to multiply a b from each of these buckets. And finally, the way that the binomial coefficient changes, and so the coefficient here is this n choose 0, n choose 1, all the way up through n choose n. And notice what we're doing is we're saying, okay, we're gonna have n buckets always. We're always choosing one thing from each of the n binomials that we have. And we're gonna choose, starting at 0, 0 b's, then 1 b, and then all the way up to n minus 1, and then eventually n of those b values. And so the binomial coefficient is changing because the number that we're choosing is increasing by 1, starting at 0 and increasing by 1 each time. So what we want to do is leverage this pattern in order to write our binomial theorem in a slightly more succinct way. And the way that we're going to do that is by taking advantage of the fact that each time that we're computing one of these terms, we're only changing a couple of things by 1, right? So notice that we're changing the power of n by 1 each time. We're changing the power of b by 1 each time. And we're going to be changing the value of k here. So n choose something, n choose k. That n choose whatever that is changing by 1 each time. And so what we can do is we can say to ourselves, well, if we're only changing a couple of things with each of these terms, why can't we just write a rule that says, hey, here's how you change the things in each of these pieces, and then we can write it in a more succinct way. All right, so here is the binomial theorem. Don't worry about this just quite yet. What we want to do is notice, as we just did, that each of these terms has 3 things in common. It has n choose something, a to a power, and b to a power. All of them have those 3 pieces. And we also notice that each of those pieces changes by only 1 as we move from term to term. So n choose k, in other words, what this value is, 0, 1, 2, all the way to n, changes by 1 and increases. The exponent of a, which starts at n, decreases by 1 each time. And the exponent of b increases by 1 each time. And what we're doing with each of these terms is adding them together. So what if we could say, hey, let's just do that. Let's add each of these terms together where you start here, and each time you're increasing these particular values or decreasing these particular values by 1. So the way that we do that is with sum notation, S-U-M, which tells you to keep adding things over and over and over again. So the way that we write it is like this. And I'm going to explain what this sum notation means with this example here. So sum notation tells you this. It says start when k equals 0. And when k equals 0, plug in 0 for k into your expression. So I just have a very simple expression here. This is just saying a sub k is your term. Okay? So when k is 0, I'll have a sub 0. Once you've evaluated that expression for k equals 0, you then change and increase k to be 1, or 1 higher than what it was before. You plug that into your expression, and you add it to what you had before. So we'll add a sub 1. And you keep doing this, so we'll then have a sub 2. You keep doing this all the way until your k value is equal to n. Okay? So that will allow us to write our binomial theorem in a much, much cleaner way. And here's why. N choose k is starting at 0. So we have n choose k, and we're starting it when k is equal to 0. And that will give us n choose 0 as our first term. Now, we want a to some power to start out at a to the n. So since k will start out at 0 and then increase by 1 each time, if we do n minus k, we'll start at n, and each time k changes by 1, we'll decrease the power of a by 1. We have b to some power, and we want that to start at 0 and increase by 1, just like we did and choose k, because this k represents the number of b's that I'm multiplying. So I'll have b to the k. Now, if I were to follow my rule for sum notation, I would plug 0 in for k. I'd get n choose 0, a to the n, b to the 0, my very first term. Then I would change k to be 1, and I would evaluate my expression again and add it to what I got the first time. I will keep doing this until I go all the way to where k is equal to n. In other words, I'll get this last term. So this here is actually saying the exact same thing as this up here. It's just written in a much shorter form. And that's very important to remember. These are not different statements. These mean the exact same thing. This is just written in a much shorter, more efficient manner. So if I were to actually go through and execute for k equals 0, I get this first term. Then when k is 1, I get this second term. When k is 2, I get this third term. And when k finally gets to be n, I will get the last term. So using this summation notation, we can write what we're going to expand in a little bit of a shorter form. And that will just help our work stay a little bit cleaner. All right, so let's try one together, and then you will do the rest. So we're going to write each expression using the sum notation version of the binomial theorem expansion, and then expand and simplify. So let's start with this first one here. Notice that x is representing my a value, 2 is representing my b value, and 4 is representing the n value here. So my binomial theorem says that when I expand this, what I'll be doing is taking the sum starting when k equals 0, going all the way until k equals n, which in this case is 4. And the expression that I'm going to be plugging k into is going to be n choose k. N is 4. 4 choose k. Then I'll have a, which in this case is x, so x to the n minus k. X to the n, now n is 4. 4 minus k times b, which in this case is 2 to the k. All right, so now I can go ahead and expand using the rule or the way that sum notation works. So I start when k is equal to 0, so this will be 4 choose 0, x to the 4 minus 0, or x to the 4. Then I have 2 to the 0. Now I'm going to change k by 1. It's going to go up by 1. It's going to go to k equals 1. And I'm going to evaluate the expression again and add it to what I have already. So I'll have 4 choose 1, x to the 3, b 2 to the 1. Plus, and now I'm changing k to be 2, so on and so forth. So I have 4 choose 2, x to the 2, x squared, 2 squared. All right? Plus, I'm going to go down to the next line, but you should be able to keep this on the same line. Now k is 3, so I'll have 4 choose 3, x to the 1, because, again, k is 3, so I'll have 4 minus 3, which is 1. 2 to the k, so 2 to the third. Plus 4, choose now, k is 4, x to the, and now think about this, k is 4 now, so I have 4 minus 4, or x to the 0, 2 to the k, which is 4. So now I can go through and simplify once more, because I can compute 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4, and 2 to all these powers. Go ahead and try that on your own and see that your answer matches up with mine. So I went through and I computed my 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4, and also multiplied it by whatever I got for my 2 to the certain power. So here 4 choose 0 is 1, 2 to the 0 is 1, so I just have x to the 4th. 4 choose 1 is 4, 2 to the 1 is 2, 4 times 2 is 8. 4 choose 2 is 6, 2 to the second power is 4, 6 times 4 is 24. 4 choose 3 is again 4, 2 to the third is 8, so I have 4 times 8, which is 32x. Then 4 choose 4 is 1, x to the 0 is 1, and 2 to the 4th is 16. So that would be my final expansion. I want you to go ahead and practice with each of these, 2 through 4. Your work should look just like our work does here, with the only difference being the different values that we have. A couple things to take note of. Here we have -1 as the b value, and here we have -x as the b value. So make sure that you're incorporating that negative when you're evaluating. First, write it in terms of your sum notation. You want to get used to this because it's actually a really succinct way of writing some very long, complicated things.